Welcome to the Mahatma Gandhi Institute of Technical Education and Research Center. In 2004, a national level institute MGITER has been started in the field of engineering and technology as per guidelines of All India Council for Technical Education AICTE New Delhi. MGITER is approved by AICTE New Delhi, Gujarat State and affiliated to Gujarat Technological University Ahmedabad, which is also known as GTU. Our goal is to be an institute of generative ideas so that we remain relevant to our society. The MGITER has always been an organization on move with continuous effort on improving its processes and to maintain its relevance to the Indian science scenario, with adding new programs in its programmatic portfolio. We strongly believe in overall development of students, so for that we provide them a different platform like state level tech fest, project fair, different sports activity, which helps students to teach teamwork and problem solving skills, to get physical health benefits, boost self esteem, and reduce pressure and stress for prove their skills in distinct area. Welcome to the virtual class of Professor Gaurang Patel. Today we are going to learn the subject design of AC machine. Okay, today what we are going to learn, these are some of the contents that you can see over here. That is output equation of an induction motor. Then we will move towards the calculation of main dimensions, shapes of stator slots, stator conductor cross section, stator slot pitch, length of mean turn, stator teeth design, and stator core design. One by one topic we will cover it throughout this lecture session. So so before going further, we just recall whatever we learned in the last lecture session. In last lecture session, we just go through the basics of the three-phase induction motor. In that, we had learned that there are mainly two parts in three-phase induction motor. That is, one is known as the stator, which is a stationary part of the device, and second that is known as the rotor. This is the rotating part of the device. Okay, so in that we can say that the AC induction motor comprises two electromagnetic parts. One we already discussed, that is stator, which is a stationary part, and second one, that is the rotor, which is a rotating part. So the stator and the rotor are each made up of an electric circuit. Both those parts are made up of electric circuit, and which is usually made up of insulated copper or aluminum winding to carry the current. In both of them a magnetic circuit is there, and it is made up of laminated silicon steel to carry the magnetic flux. So for the output equation of induction motor, what is output equation is exactly, we can say that output equation is the mathematical expression which gives the relation between the various physical and electrical parameters of the electric machine. Okay, once again I will repeat this, that output equation is the mathematical expression. Okay, output equation is the mathematical expression which gives the relation between the various physical and electrical parameters of the electrical machine. So in output equation we will see what. So those are the contents, and now we are going towards the output equation of the induction motor. So okay, so in output equation of induction motor we can see that there are main terms we are used over here, that is q is equal to c0 d square ln kW. Okay, so if you look at the output equation, we could get it as Q is equal to 0 C0 d square ln kW. In kW we generally taking in terms of kilowatt. Okay, so if you look at the terms which is present here, I could say that C0 is equal to output coefficient, which is generally given by 11 BAV AC kW into 10 raised to 3. So over here that is the C0 which is given into 11 BAV, that stands for average flux density, AC kW into 10 raised to 3. Okay, over here kW, all the terms are given here. AW, kW, which is the winding factor, AC, that is the specific electric loading, and BAV, that is a specific magnetic loading. Okay, in case of transformer, kW was there and it stand for window space factor. So in case of transformer, kW that is stands for window space factor, but in three phase induction motor we are considering kW as a winding factor. Okay, then we also have the formula with the relation between HP and kW, that is the relation between HP and kW. So here we consider Q is equal to HP into 0.746 into efficiency into power factor, where cos 5 stands for the power factor. So this is the output equation of three phase induction motor. Next we consider choice of average flux density in air gap and choice of ampere conductors per meter. So when we calculate the output equation of three phase induction motor, those are the things that we have to keep in mind. That is choice of average flux density in air gap, then choice of ampere conductors per meter. In that we have to consider that power factor, iron loss, overload capacity, copper loss and temperature rise, voltage and overload capacity in the three phase induction motors. So those parameters we have to keep in mind when we design the three phase induction motor and when we calculate the output equation of the three phase induction motor. Okay, so from the output equation we calculate the value of d square L. From the output equation we calculate the value of d square L. So just a moment, I just make it correct first. Okay, over here. Okay, that's fine. Now we can proceed further. So from the output equation we calculate the value of d square L over here. So all the other term take on the one side, okay, and d square L will take on another side. So once we calculate the value of d square L, then our work is to calculate d and L separately. So now we have to separate it out, this term d and L, and we have to calculate it separately. So where we use the ratio of L by tau, that is the ratio of L by tau. So the ratio of L by tau when we consider, so it stands for pole pitch. This ratio stands for the pole pitch. And what is the pole pitch? I hope you all know. So pole pitch is the distance between the two poles. Okay, now then the relation for different designs between L and tau are given. So over here there is the relation between L and tau for the different designs are given. So whatever the specific need, as per that we have to consider the ratio of L by tau. Okay, so when L by tau is equal to 1 is considered, that is considered for good overall design. When it will be considered in between 1 to 1.25, so our aim is to design the motor for the good power factor. Then when it is equal to 1.5, so our aim is to calculate that motor for the higher efficiency. And when it is in between 1.5 to 2.0, so it is design we will consider in overall economical design. Okay, so that's how the value of L by tau is considered. So when we got the value between L and tau, this L by tau value, when we decide or when we got, then this easy to calculate the value of D and L. As we have the two equations now, one will be the equation starting with d square L and another equation is L and tau, giving you the relation between L and tau. Then if we look at the further part, so in general the value of L by tau is lies between 0.6 and 0.2 depending upon the size of machine and the characteristic desired. Okay, so it is generally lies between 0.6 and 2. Okay, so for normal design the diameter should be so chosen that the peripheral speed does not exceed about 30 meter per second. Okay, so now so this diagram is shown the calculation of main dimension for induction motor. Over here the cut section of front view and the side view shown here in this diagram. With these views I could say uh, one minute, I could say here this is the front view. Okay, this is, I can say this is the front view of the diagram, and this is the cut section of the side view. This, you can say, this is the cut section of the side view. Okay, so with these two views I can understand the relation between different things related to the design of three-phase induction motor. Okay, like if I look at something, what we said diameter of bore, so we need to understand first of all presented in this diagram. Okay, so when we consider the bore of that diameter, okay, this is the representation of diameter D. So this is the represent that innermost of the shaft of the induction motor. So this is the innermost part of the shaft of the induction motor, which is also shown in the side view. Okay, in side view there is a shaft of the induction motor. This is the side view and this is the front view. Okay, this is the side view and this is the front view. So over here, so here representing of these two things, that is we already discussed, that is the innermost diameter shaft of the diameter. In side view we can consider this is the shaft of the induction motor. Here representing the motor shaft, this part is motor here, and then after a rotor there is a part called stator, which is steady in nature, we know that. Okay, so this is the representation of the stator. Okay, this is the representation of the stator, you can easily understand from the figure. And the diameter of stator is inner diameter of the stator, which is represented here, that you can identify with the small d. Okay, so when we consider, so over here there is the small d, this diameter of small d, which is representing the diameter of stator bow. Okay, so we need to understand in between stator and rotor there must be some air gap. is also represented there, and easily identify the air gap as well. Okay, so inside side view, it is very easy to understand. This is the central line which is shown is a axis for the motor, then could be a shaft. Okay, so here this is the central line. Okay, this is the central line which is shown here. It is the axis for the motor. So once you represent the stator bow, then we have to represent the rotor part. This is the rotor part. This is the complete part is known as the rotor part. So we can easily see in the side view of that diagram. Or so in between a rotor and stator, so this is the rotor and this is the stator. In between you can see this is the D, which is considered as the air gap. Okay, so from that explanation I hope you can understood what is which one is the part of which one is the part of a rotor and which one is the part of stator. Also you can understand what is the air gap. So for that, some of the relations are given for the length of air gap. For the del is equal to 0.2 plus square root of dl. What is d and l, I hope you know very well from this explanation. So for the d and l are in generally considered in the meters, and for medium rating machines del is considered between 2 to 3 mm. So these are the calculation of main dimensions. Okay, now we will move further. Now we consider the design of stator. Okay, so in design of stator we can see over here, that is the stator conductor cross section. So for that, the current density in the stator winding is usually between the 3 to 5 ampere per millimeter square. Okay, so the stator current per phase is given over here, that is is equal to q into 10 raised to minus 3 divided by es. Okay, so over here the next term, that is as, which is stands for area of each stator conductor. So area of each stator conductor is given by the is by del s mm square. Okay, and then as we discussed, that is del s, that is usually considered in between 3 to 5 ampere per meter square. Okay, so what is the given over here? That is given over here the value of is. Okay, and the equation for the as, and as we discussed, that is as stand for the area of each stator conductor, that is stands for the area of each stator conductor. Okay, then we will also discuss regarding these things, that is del s. Okay, so del s, which is considered in between the 3 to 5 millimeter square. Okay, so for del s current density in stator conductors, what del s stands for? Del s stands for current density in stator conductor. Okay, so you can easily understand when you are going to calculate the stator conductor cross section. Okay, so the for lower values of current, round conductors would be most convenient. Okay, so to use, while for higher currents bar or strip conductors should be adopted. For the higher currents we should use the strip conductors. Okay, when we use the strip conductors, so you can use the strip conductors for the higher value of current. Okay, so at that time conductor should be adopted as anything about 2 or 3 mm. You can consider the area for the 2 or 3 mm in diameter. Okay, so the use of bar and strip conductors gives a better space factor for the slot. So when we use the bar and strip conductors, what is the advantage of bar? 1 minute. What is the advantage of bar and strip conductors? Bar and strip conductors, which is give you the better space factor. Okay, which gives you the better space factor. This type of question can be asked in the viva examination as well. Okay, so examiner can ask which kind of value diameter which will give you the better space factor. So you can consider there is a bar and strip conductors in between 2 or 3 mm. Okay, so now, so over here we will consider the area of stator slot. So in this diagram we can see in area of stator slot there is one equation that is given over, that is approximate area of each slot. Over that is approximate. When we consider the approximate area of each slot, then we consider the copper area per slot divided by the space factor, that is equal to ZSG. Well, when ZSG, which is given or which is stands for the conductors per stator slot, that is ZSG, that is stands for the conductors per stator slot, and AG, that is stands for area of each conductor divided by the space factor. Okay, so over here this is dimension is given, that is DSS, which stands for DSS, that is the diameter of stator slot, and that is the width of stator slot. So when you consider the area of stator slot, the space factor ordinarily varied between 0.25 to 0.24. Okay, so now we will see the space factor over here. Just a moment, I will show you one by one. So when we consider the space factor, so what we keep in mind, that is it should be considered between the 0.25 to 0.4. Okay, so when high voltage machines have lower space factors owing to the large thickness of insulation, when we consider the case of HV machines, okay, then we must be consider the thickness level of insulation should be large. Okay, after obtaining the area of the slot, the dimension of the slot should be adjusted. Once we obtain the area of the slot, once we obtain this area of the slot, then we can or adjust the dimension of the slot. Okay, so the tooth width and the slot width at the gap surface should be approximately equal. So the slot should not be too wide or to give a thin tooth. The width of the slot should be so adjusted such that the mean flux density in the tooth lies between 1.3 to 1.7 Weber per meter square. Okay, so when you select the width of the slot, what I have to try to make you understand, that is when you select the width when you select the width of the slot, the the flux density value, which value you have to consider, that is flux density value, which must be lies between 1.3 to 1.7 W per meter square. So the width of it should not be too large, as it results in narrow and deep slots. The deeper slots give a large value of leakage reactance. In general, the ratio of slot depth to slot width should be between 3 and 6. So the ratio which is we have to taken between the ratio, what ratio we have to taken between 3 and 6. Okay, so that's how we can find the area of stator slot. Now let's we just revise the terms which I already discussed with you. So those are some of the important terms that you can consider while you are designing the particular design stator winding. Okay, so first of all, that is the current density of stator conductor is usually assumed between 3 to 5 round conductors. Okay, the next one, that is the shape and size of slot has an important bearing on the performance of an induction motor. And the last one, that is the mean flux density in the tooth normally lies between 1.2 to 1.7 Weber per meter. So the ratio of slot depth or slot width is kept between 3 to 5. So up till now, whatever the query, if you had in this session, you can free to ask me. Okay, so now we discuss the question asked in GTU examination in previous years. The first question was asked, that is derive the output equation for relationship between rating and size in case of three-phase induction motor, which was asked in summer 2014. And the second question, that is asked derive an output equation for three-phase induction motor with usual notations. Though so this second question was asked repeatedly, you can see it was asked in summer 2018, 2014 and winter 2017 and 16. Okay, so once again I would like to say you that if any query regarding those question and answer, please ask me. Okay, thank you.